Hi everyone, so today we're going to be starting a new project and I'll be taking you guys along for the ride. Okay, so what exactly are we trying to do? Well, let me tell you. So today we're going to be trying to look at how to create realistic fluid simulations. Specifically, I'm talking about fluid simulations in games. So whenever there's a really good fluid simulation in a game, whether that be a body of water, smoke, maybe some other kind of fluid, it makes the experience all that more immersive, whether a player notices it or not. I really enjoy game development, and this aspect of it is something that's interested me for a while. But before we get into the actual simulations, we need to start thinking about how we can actually create these fluid simulations. This topic is something that people have been studying for a really long time, so we can learn a lot from looking into the different methods that other people use to create these fluid simulations. And whenever I was looking into this, there was one set of equations that kept showing up wherever I looked. These equations are called the Navier-Stokes equations. So let's take a look at what we're working with, okay? Okay, so maybe this seems a little bit confusing at first glance, but let's take a step back and talk about what these equations are even used for. Well, these guys are actually universal laws of physics, and believe it or not, they're used to model literally every single fluid that we have on Earth. It's a way to predict the way that different fluids behave, and when I say fluid, I don't just mean liquids. It's also talking about some gases and even some certain solids. If you've heard of these equations, it's probably because it's one of the 7 Millennium Prize problems. If you solve any of these problems, you get awarded with a $1 million prize, and the Navier-Stokes equations is one of them. And that's because we actually don't know a whole lot about these equations, despite the fact that they're used very heavily. But we won't get too deep into that right now. Let's just look back at these equations. So what's even going on here? Let's start by looking at this first one again. So this is actually just conservation of mass. So let's say that we have a fluid. Let's say that it's a body of water. It could move around, it could change shape, but we're not adding anything and we're not removing anything either, so the mass stays the same. Thus, mass is conserved. So let's take a look at the second one now. If we take a step back and break this down a bit, at its core, this is really just Newton's second law. So mass times acceleration equals force. And of course, it's a bit more complicated than that, but that's really all we need to know for now. I'm just setting you guys up to understand what kind of stuff we'll be dealing with when we're trying to simulate fluids. And many fluid simulations actually use a simplified version of the Navier-Stokes equations, but we'll get a little bit more into that later. Okay, so let's take a look at the 3 main methods for simulating fluids in games. So the first main method that's used is called procedural animation. This is good for larger bodies of water, such as oceans. The way that this works is you don't solve any physical equations, so what you're really doing is you're just simulating the effect on the water instead of the actual cause of that effect. This gives you a lot of control, but since you're just simulating those effects, it often doesn't work as well with other objects in the world, and it usually doesn't look as realistic as some other physics-based methods. So the second method is called particle-based fluids. So the way that this works is the fluid is represented by a set of particles. This allows you to render the fluids really quickly. It's good for sprays, stuff like that, even blood splats, but it's not good for larger bodies of water such as lakes, rivers, oceans, etc. Now let's look at something in the middle. So this is called a height map. So the way that this works is you simulate fluid just by focusing on the surface of the water. This is really good for kind of middle of the road, contained bodies of water such as rivers, lakes, and ponds. And the way that this works is you just look at the surface of the water, so it turns your 3D problem into a 2D one. So what does this have to do with the Navier-Stokes equations? Well, let's think about partial differential equations in general. The way that this works is whenever you're using a partial differential equation, it allows you to track each individual point on a surface and track how it changes over time. And that's exactly what's happening with our height map method. So let's consider this on a smaller scale. So let's think about just a kind of one-dimensional use case of this. We have a body of water that is represented by some different columns, where each of these columns is a point on the water. So the point, this bar will move up and down according to the velocity as it changes over time, and it'll change the column height per time unit. And this is something that is pretty interesting because it works on a small scale, and all we have to do is pay attention to the force, mass, and acceleration, as we mentioned before. And so we can extrapolate this a little bit further. With partial differential equations, we can just use this on a kind of 2D scale that can be used as a kind of 3D thing. So like I said before, height maps allow you to just kind of look at the surface of the water. So imagine that every single point on the surface of the water is just represented in some way. So that point has its own kind of velocity and it's whatever force, pressure that you are paying attention to. And so when we're given those units and we give it to our Navier-Stokes equation, or in this case, it's a simplified version, then it will be able to predict what will happen in the next point in time. And it looks at these, usually whenever the partial differential equations work like this, they're looking at the neighboring adjacent columns, and it's kind of adjusting itself depending on that. And that's pretty much what we're doing here. So the surface will change, and we'll just have all of the water beneath that, but we won't need to pay attention to any of that. Like I mentioned before, there's a lot of stuff that we can take out that we don't need to think about whenever we're making these kinds of simulations, that the Navier-Stokes equations need to think about a little bit more. Things like this include viscosity, so like the thickness of your fluid. So like water would have less viscosity than something thicker like honey or maple syrup. Another thing that's kind of a main issue, I guess, with the Navier-Stokes equations is this idea of turbulence. So if you've ever experienced like turbulence on a flight, for instance, whenever there's the air just suddenly starts becoming a lot more unpredictable. Or for instance, we'll have some body of water and at some point in time we'll have some turbulence where the water does something completely unexpected. And this is the kind of question that a lot of people that are studying the Navier-Stokes equations are trying to answer. But whenever we're just doing these kind of smaller simulations, it's not something that we actually have to worry about. And there are a lot of other things that we need to think about as well whenever we're making these kinds of fluid simulations. A lot of times, fluid simulations can be very taxing on a system if you don't do it well. Whenever we use something like height mapping, it actually reduces this problem quite a bit because you're just worrying about the 2 dimensions instead of the 3 dimensions. But there's still a lot there, and you need to think about memory, you need to think about making it faster, and just all of that is really important to pay attention to. So there's a lot of different ways that people try to mitigate this problem. One of the main ways they might try to do it is just by lowering the resolution. But this makes a lot of the details disappear and just makes everything look a lot more blobby and just not as good overall. Some other stuff that is used would be changing the level of detail depending on how close or far away you are from the given object, so only making things high resolution whenever they're within a certain radius of the player, and then things that are further away would become lower resolution. And then obviously there's a lot of other stuff you need to think about with game development, especially with how your water is going to be reacting to other rigid bodies, other objects in the world, if that's something that's going to happen. It needs to remain stable no matter what you throw at it. And then obviously another thing you have to think about, other than just the way it's moving, is thinking about reflections on the water and how that works, and refractions for the things that are inside the water. As you can see, there's a lot of semantic stuff when you're thinking about fluid simulations. There's a lot more that we didn't even talk about. But this is really mostly what I was planning on covering today. As we continue throughout this, I'm going to actually try to start building some of these fluid simulations myself, and we can kind of see what happens with that. I hope you follow along. Thank you so much for listening to me. Thank you so much for watching this video, and I hope you have a great day. See you next time.